In this chapter, we're going to take another look at energy, but instead of looking at energy as heat, we're going to be looking at energy as electromagnetic radiation. And to understand fully the historical context of this chapter, it's important to understand what's known as a classical view of the universe, and is considered classical because it's an idea that was held since the time of ancient Greeks. The classical view of the universe is that the universe is made up of matter and energy, and matter and energy are two distinct things. Matter is defined as something that has mass and volume, and energy doesn't. And if we remember back at the beginning of our chemistry class, we actually used these definitions to distinguish between matter and energy. However, as we'll see later, energy and matter are just different forms of the same thing. Now, in chemistry land, we use the word light interchangeably with electromagnetic radiation. In our everyday life, when we're talking about light, we're talking about visible light. But I just wanted you to be aware of that. When you see light in chemistry land, it could mean any type of electromagnetic radiation. Electromagnetic radiation is a type of energy transfer, and electromagnetic radiation is made of waves. Or actually, I should say, it can be described in terms of wave behavior. Now here is some examples of visible light. Anything that we see is an example of visible light. And when we're looking at fireworks, often we'll hear the popping if they're far away from us much later than we actually see them. The same is true of thunder and lightning. We see the lightning before we hear the thunder, unless it's right above us. That is because light travels 1,000,000 times faster than sound. Light travels 3 times 10 to the 8th meters per second, and sound travels about 300 meters per second. Both travel through waves. So let's look at some characteristics of waves. Waves always have some sort of speed. They have a height, which is known as amplitude. They have a length. And then we also care about the number of wave peaks that pass through a certain point in a given amount of time. Now, what makes electromagnetic waves, electromagnetic radiation, is all electromagnetic radiation travels at the same speed. This speed is known as the speed of light. It is abbreviated by lowercase c, and it is 3 times 10 to the 8th meters per second in a vacuum. All electromagnetic radiation travels at this speed. And as far as we know, at this point, this is as fast as anything can travel. So the amplitude is the height, and the wavelength is the measure of the distance covered by the wave from one crest to another. So let's look at an example here. Here's an example of a wave, and this is similar to a wave we might see at the ocean. The top part is. The disturbance in the water goes up, and the wave travels in a direction that's perpendicular to the way that the disturbance is. Electromagnetic radiation is the same. Here are the waves, or the disturbance, and they're traveling in a direction that's perpendicular. So here it's going up and down. That's where our disturbance is, but it's traveling this way. Okay, now the amplitude would be from here to here. That would be how high the wave is. And then the wavelength would be crest to crest, or trough to trough, or really any point to an identical point. They're all going to be the same. But just for simplicity, we typically just look at crest to crest. We use this Greek letter lambda, and L for length, to abbreviate wavelength. And it is an actual length, so it's going to be some unit of meter, either a derived unit of meter or meter itself, when we're characterizing wavelength. And since this is characterizing an electromagnetic wave, the speed is 3 times 10 to the 8th meters per second. Frequency is another characteristic. This is how many waves pass a point in a given period of time. So if we look back up here, we'll choose a point, and in a second, how many waves go by this particular point? Okay. All right. Frequency is abbreviated by this Greek letter nu. This is the Greek letter N, and it looks like an italic V, but it is a nu. And as I said, it's the number of waves that pass a given point in a period of time. It's often in physics represented by numbers of cycles. That's how they call it in physics. But in chemistry, we use the unit of reciprocal seconds. How many per second? Hertz is equal to a reciprocal second, and this little -1 as a superscript means per second, or 1/second. So we could also write this 1/second. That would be the same as this. Now the energy of a wave is proportional to the amplitude and frequency. We're going to be focusing more on the frequency though. The larger the wave amplitude, the more the force it has, and if we think of an ocean wave, that makes sense. A tidal wave has certainly more force than a smaller size wave. And the more frequently the waves strike, the more total force there is. So the higher the frequency, the higher the energy. So let's look at an example here. Here is an example of a low frequency wave. If we look at a given point, because of the long wavelength, not that many waves are going to go by in a given amount of time compared to a shorter wavelength. So this would be a high frequency wave, a high energy, and this would be a low frequency wave and a low energy. Now notice that the wavelength is opposite of the frequency in terms of magnitude. If we have a low frequency, we have a long wavelength or high wavelength. If we have a high frequency, we have a low wavelength or short frequency. So wavelength and frequency are inversely proportional to one another. As wavelength goes up, frequency goes down. Long wavelength, short frequency. As wavelength goes down, frequency goes up. Short wavelength, high frequency. And the relationship between frequency and wavelength is determined by the speed of the waves, but since all electromagnetic radiation has the speed of light, this is the relationship between wavelength and frequency for all electromagnetic radiation, where c is the speed of light, 3 × 10⁸ meters per second.